All right, so we have a spring that's, we have a block that's connected to a spring. I'll draw it this way. I've been drawing them the other way before, but it doesn't really matter. So the spring constant is K is 100 newtons per meter. There is a 3 kilogram block here. And then on top of it is a 1.0 kilogram block. Now it's gently pulled 2 meters away. So we're going to stretch it 0.2 meters away. And then it doesn't slide off. And the coefficient of static friction, the mu s, is 0.6 between the two blocks. So it's very similar. Okay, very similar to what we did in the lesson about like kind of this area. So how much work was done to pull the 3 kilogram block? So we got to pull the 3 kilogram block. Now think about the energy in the system, right? When we're doing work on this thing, we're having to fight the spring. But basically the work we're doing is going to cause a change in energy. Now you can think of it as force times displacement. However, the problem is the force, as the spring stretches, the force is getting tougher. Right, so it's hard to do the force times displacement because the force is not constant, right? I can only use the F delta X if the force is constant. So instead, think about the work causing a change in energy in the system. So I'm doing work on this block and spring, and what energy am I giving to the system is spring potential. I'm not really making this go fast, not a lot of kinetic energy, mostly just spring potential energy, okay? And then there's no energy it starts out with. That's the change in energy. So we're just going to do 1/2 times the spring constant times how much we stretched it by. So the work that I did gave energy to the block spring system, right? That's how we're going to get this thing started. And so that's going to be 2 joules of work. Systems released from rest undergoes simple harmonic motion. So it's going to oscillate back and forth. The 1 kilogram block does not slide off of the surface of the 3 kilogram block. What is the force of static friction between the 2 blocks immediately after the system is released? So right now we're at this point, we got to think about what the force of static friction is. What does that imply is drawing a free body diagram. If I'm asking you about forces, a lot of times we're going to say, if you don't know where to start, we're going to start with the free body diagram. So let's think about the 1 kilogram block on top here, right? So think about, we have gravity, 1g. We have a normal force caused by the 3 kilogram block, so I'm going to call it Fn3. And then, now, what's the acceleration? The acceleration is to the right, okay? Because this block is about to accelerate to the right? When I let it go, it's going to accelerate to the right. And what force is doing that is the frictional force, static friction. Static friction is very tricky. If there were no static friction, what would happen is the bottom block would slide out and the top one would just then fall down. Okay, so what keeps it going to the right is going to be that static friction there. And then let's look at the 3 kilogram block. This one's a little bit harder to draw the free body diagram, but just kind of go through the rules of the free body diagram. We have gravity. Then we think about everything that's touching it. We have the ground here. That's normal force from the ground. Then we have another surface here. Normal force from there, that's a surface, so it's going to push outward. And it's going to equal this Fn3 because Newton's third law of motion, right? If the block pushes up with Fn3 on the little block, then the little block pushes down, equal and opposite on this guy. That's why I'm going to label them both Fn3. But also by Newton's law, because of the surface, where the bottom block exerts a rightward force on the friction, that means this guy has a leftward force due to its friction. And then we also have the spring doing it. We've stretched the spring out, so the spring is going to the right. Because it wants to, remember the rule for the spring is it wants to go back to its relaxed length. So we're going to point back towards the relaxed length. Okay? Now in both of these systems, the acceleration is the same because they're not slipping relative to each other. So they have the same acceleration. So then we're going to do F net equals ma. Now be careful. Static friction does not equal mu Fn. I can't believe that's a very, very common mistake to make. Static friction is not mu times the normal force. Okay? You don't know what that's the maximum static friction. If I do mu times with the normal force, that's the maximum static friction. So when I do F net equals ma in the x direction, it's just force of friction equals the mass of the object times the acceleration. And in the y direction, you'll have Fn3 minus 1g is equal to 0. If we say right is positive, up is positive. Why 0? Because there's no vertical acceleration. The acceleration is only horizontal. Okay, so that's our equations there. Now, I don't know what the static frictional force is because I don't know the acceleration. So then let's look at this one here. So if we say right is positive, in the x direction, this is going to be the spring forces to the right and the force of friction to the left, and that is 3 times A. Okay, the spring force is kx. So we know kx is equal to, kx minus the force of friction is equal to 3A. And I know k, and I know how much I stretched it. So this is 100 times 0.2 minus force of friction equals 3A. And look at these two equations here. I have two equations and two unknowns. Okay, I can solve that, right? So what we're going to do is, it's easier if let's see. A is equal to force of friction, so I can just get rid of the A and make this 3 force of friction is equal to negative force of friction. 100 times 0.2 is 20. We can add the force of friction over there, FF, and get 4 of them. So that means the force of friction has to be 5 newtons. Okay? Now, what's the minimum coefficient of friction that will allow the blocks to oscillate without the 0.1 kilogram sliding off? So now we're going to say, if we want this to be the minimum amount of friction, then we're going to say, well, then this FF, this 5 newtons, is going to equal the maximum static friction that there is. And that would be mu s times Fn3. Why Fn3? Because the friction exerts here, so I care about the normal force between these two surfaces, which is Fn3. Remember, Fng is the normal force with the ground. That's not where the friction is. It's between the blocks, and that's where Fn3 is acting. So this is 5 is equal to 0, is mu s, and Fn3 was just equal to g from this equation here. Okay, equals g, so mu s is equal to 5 over g. And what's 5 divided by 9.8? I get 0.51. Okay. Suppose at one end of the oscillation cycle, when the blocks come to a stop for an instant, the top block is lifted vertically without disturbing the bottom block. The period of the system is going to change. Why? Because the period is 2 pi root m over k. So if I remove the mass, if I make the mass less, I'm going to shrink the mass. It's on the numerator, and I take the square root still smaller, then the t will decrease. Okay? The amplitude of the oscillation, now let's think about it. So it comes to stop for an instant. When does it come to a stop for an instant? Is at that 0.2 meters, when the velocity is 0, right? At the very end. So then if I remove it, the amplitude's still the same. That's the furthest it's going to go, right? The 0.2 back and forth. So it's going to remain unchanged here. And then relative to the original system, the 3 kilogram mass maximum speed. Well, let's think about it. The total energy is going to be the same. Why? Because the spring at the very end, when I remove the 1 kilogram block, we still have the same maximum spring potential energy, right? We still have the same amount. The 1 fkx squared hasn't changed. All right, so that part's the same. Whatever. So it's still the same number of whatever joules it is. Okay, I didn't calculate, I guess. Or 2 joules. Right? Still 2 joules because the spring is still stretched the same amount when I remove this block. Okay, so that means it's the same total energy. Now, however, that's equal to 1/2 mv squared. But now the m is smaller. This is a smaller m because I've now removed one of the blocks. The spring potential is the same, energy is the same because the spring is still stretched the same amount, same spring constant. However, more of that energy, when I convert to kinetic energy, will be the same amount of kinetic energy. But because we have less mass now, it's going to be a greater speed because it is the same amount of kinetic energy. Okay, so less mass but same kinetic energy, the v is going to go up.